Hey everyone, so I just want to record this quick video because I think I did not explain properly how that method works, and some of you were having a confusion about the Fermat's factorization method, and some of you did figure out how to factor an integer, a positive integer, using the Fermat's method. But I just want to give you a theory behind it. Not a theory, or just giving a working algorithm, how this algorithm works. Now, it doesn't always work. It works for odd integers. For even integers, you have to factor the two powers of 2 out, and then you can apply the Fermat's factorization here to find the prime factors for the remaining odd part of the even integers. For prime numbers, this method doesn't work. It just shows you that, oh, 3 will turn out to be 1 times 3. And that's where I was struggling when I was trying to explain it to Sean from class. So let's begin with an example, okay? So that we know how to apply this method, because you'll have a homework assignment on this. So suppose I pick my integer to be 5959. Okay, it's a very classic example. I want to factor it using Fermat's method. Now Fermat's method worked by using the difference of squares. So writing this number as a difference of squares, where then you can find the factors based on that. That's how it works. How do I begin finding that a? So you first find the square root of your given integer. Find square root of this. Approximately gives me 77.2. We round up always, okay? We take our a to be a fixed point 78. Alright, and now I have to compare my b square. So according to Fermat, n equals a square minus b square. For some b, n is this, and a is 78 squared, and I have to look for the b square, and I need a b square that works out, right? So I'll keep increasing my a and see which one fits. So here's the algorithm part. This is how the computer will run it. So step 1, I'm going to check it for a equals 78 if I find a nice b. So n, which is 5959, should equal a square minus b square. Solve for b. The b square will be 6084 minus 5959, which is 125. Now this is not a square, this is cube of 5, so I can't express this as b square. So this is not the iteration. This is step 1. Iteration 1, I'm moving on to iteration 2. So I pick for a equals 79. Now I'm looking for a proper candidate, a potential candidate, b square. So again, 5959 should equal a square minus b square, right? And when I solve for b square turns out to be 79 square, which is 6241 minus 5959. Of course, you need a calculator for this. 282. Again, when I find the square root, it is not a perfect square. Not a perfect square. So let's go with 80, right? You keep increasing the a. So third iteration, I go for a equals 80. And now I look for a potential b square. Let's see if I have one. So I do 80 square minus b square. When I simplify for b square, I get 441. And when I do the square root, I get b equals 21. Bingo. So for a equals 80, I have a b equals 21. So according to Fermat's, 5959 equals a square minus b square, which is nothing but a minus b, a plus b, right? And a that works turns out to be 80, and b that works turns out to be 21. 80 plus 21. And then you have to check, because there are a few cases which I have heard of. I can't find an example to show you guys, where the given factor doesn't turn out to be a prime number. So we must check, okay? Check 59 for primality and 101 for primality. In this case, they're both primes because I've checked them. You know how you check for primes? You do the square root of 59, whatever that is, and you try to divide it by any prime number less than the square root. So let me quickly find the square root in my calculator here. Calculator square root, wait, sorry, how do I do this? So square root of 59, okay? I'm getting 7.68. So I'm going to try dividing 59 by every prime number less than 7. And you can clearly see it's not divisible by any of them. So 59 is a prime. Same thing you do for 101. But this is how the Fermat's factorization method works, and I thought I should upload a video before I give you homework. Okay, have a good week, everybody. Thank you for your attention.